Oh, hey, a microphone, even better. And then I went off. I was actually a professor at a small liberal arts college at Oberlin, and so I got tenure at Oberlin, and then I decided, maybe I'd do something a little different. So I did the AAAS Congressional Fellowship. I worked in the US Senate for a year doing science policy. And from there, I ended up at the Kavli Foundation, where I've been doing not just astrophysics, but nanoscience and neuroscience and all sorts of bizarre things. So if you want to learn about all of these possibilities, come chat with me. Sorry, that was the fast introduction. I was too fast for
So, good to see you all here. Exciting for our last set of lectures, and we'll start off with Priya.
Thank you so much. So, thanks everyone for staying the course and coming on Friday morning. So, what I wanted to do today was, as promised, I want to wrap up to show you how we actually use the kinds of approximations and scaling relations we obtain from physical modeling of accretion processes around a black hole into the larger framework of understanding the growth of black holes over cosmic time. So remember, what we did was calculate these scaling relations by trying to look at the gas accretion processes, model feedback, geometry of the disk, sort of zoom in. And this is for sort of a template for an individual galactic nucleus. So from that, we extract these scaling relations. And the goal is eventually, as you'll see, the attempt is to do demographic modeling of the whole of a population of black holes as a function of cosmic time. So ideally, the storyline that we want to build is to start from a model for the formation of the first seed black holes, and then we embed them into the cosmological context and use the various scaling relations that we've developed, play with the various scaling relations for different kinds of accretion, accretion laws, and different prescriptions for feedback, and then see if we can best fit the data. Part of why we're doing this is the most compelling data sets that we have for accreting populations of black holes are the luminosity functions in redshift bins now. So we really have, and we have multi-wavelength data, as I'll just show you, right? So we have a lot of interesting constraints that any model that you start out with, obviously, ingredients of the model are guided by what we see, but the question is, when you put all the ingredients together, can you simultaneously match all the data sets? So the goal is not just to match the luminosity function of quasars, distant quasars at redshift 6, but to see what set of physics, what set of scaling laws, what kinds of accretion models will consistently allow you to match the observed luminosity function at 2, 3, 4, 5, and 6, and then match with the integrated emission of these sources and match the constraints of the cosmic X-ray background, which is the sum of all the photons emitted in the X-rays from these accreting sources, and so on. So this is an approach. I mean, this is obviously not new. This is an approach that was really pioneered by Guinevere Kaufman and Rachel Somerville. And it's sort of, and over time, we've been building it in sophistication in terms of connecting sort of physical models, improving the physical models, and then adding these ingredients back onto this population. And so there are three key aspects, as you'll see. And the first is the physics of seeding, which I did not talk about yet, so I'll talk about it today. So how do you what are the arguments you can make? And the reason I say arguments is because, once again, not all the multi-scale physics is computationally feasible at the moment. There are bits and pieces that are doable, and I'll show you where we are with that. So we have channels that we think are viable ways to make the seed black hole. So there's the seeding, there's the uncertainties associated with seeding physics. Then we have the accretion models, and you saw that there's uncertainties that are associated with the detailed physics. So we extract some scaling, but what we don't know quite precisely is whether there are particular phases for if you follow the growth of a black hole from, say, seed mass to 10 to the 8 solar masses today, say over a period of 9 to 10 gigayears. Question is, are there phases in which I showed you the two different accretion models, broadly speaking, that correspond to the luminosity, the output luminosity being proportional to the mass accretion rate directly versus the log of the mass accretion rate. So what we don't know quite yet is whether there are phases where, you have super Eddington accretion, so you have low radiative efficiency phases interspersed with phases. We think that's obviously the solution. And that's going to depend on this, as we saw, if you remember from the feedback lecture, that the domain of when you kind of switch feedback and when you switch the kind of accretion model depends on the details of the accretion geometry and the environment, the conditions in which your black hole is sitting. And that is going to vary cosmically depending on whether you're being fed by filaments and so on and so forth, right? So there's some inherent sort of uncertainty that we have, but what we want to do is to propagate these models, and that's why these semi-analytic models are so useful. They're really not as computationally intensive. They can get to be when you want to produce higher and higher resolution models and get better statistics, but nothing like the kinds of simulations that Ramil or Roman have been talking to you about. These are still doable on a desktop within a day. Like one scenario can be done in a day. And that's the advantage of these models. So you can actually play with many different recipes for many of these ingredients and see how well you match the observational data sets. And so in the third ingredient, so you have the seeding, you have accretion, the uncertainties in the seeding, uncertainties in the accretion physics. But we've bracketed everything, right? So we kind of know that the accretion is probably between these two models. As I said, you may go intermittently between the two, but the point is you bracket them. And then with seeding, again, I'll show you we can kind of bracket the choices. And then there's an important piece, which is the dynamics, which is, we now know that black holes do not primarily accrete most of their mass by actual merging with other black holes. However, that actual merging is very consequential because it produces gravitational waves. And the interesting thing about the setting in which supermassive black holes merge compared to stellar mass black holes that LIGO has detected, in the event of supermassive black holes merging, you almost always inevitably have associated electromagnetic counterparts just because of the cosmic setting in which this happens, which is galactic nuclei. This is sort of a rich phenomenology that you can do. So even though in terms of the overall mass assembly history of a black hole, direct mergers themselves do not contribute. They contribute majorly during certain phases for high mass black holes at low redshifts, et cetera, right? But overall, they are not the main way. So black holes really grow by accretion, which is why we're obsessed with these accretion models, right? And but the predictions for the gravitational wave production for LISA rates is really important because I think LISA is a reality. And I'm really hoping, I'm on the NASA LISA science team, and our goal is to, get interest drummed up within the astrophysics community in the United States so that NASA will keep up its commitment to contribute either in cash or kind to the project. And the reason this is important now, scientifically, this is very exciting. It's very clear that, this is a dead sure observation. We're going to see these. It's just a question of getting the apparatus up. So it's a question of funding and so on. And I think the more intellectual interest there is and the more we understand about the multi-messenger nature of supermassive black hole mergers, I think actually even the project can go faster. But okay, let me now today's lecture is really kind of a wrap-up, kind of pulling together of the elements that I presented in the first two lectures, sort of apply them. So before I move on, a lot of this is work that has been ongoing for the last 5 to 7 years. There's been a real spurt of activity in sort of each of these pieces. So I've been most involved very recently on the seeding part of it and the observational signature. So what we have is the seeding, accretion models, and dynamics. Ultimately, we want to have match the observations, and we want to see if we can get any discrimination between models, right? So obviously, we're going to try out all these models. So I just wanted to give a shout out first to my current graduate student, Angelo Riccardi. I'll be showing you a lot of his results today, and some really nice work that we've been doing at Yale with Fabio Pacucci, Nico Capelluti, and my former postdoc, Bhaskar Agarwal. And I mean, there are many people in this room, so I just have the names of people who've contributed to these 3 pieces that I'm talking about, what I think were really important, interesting, recent papers. It's obviously not an exhaustive list, but there are many people in this room. So Rachel and Andrea have done a lot of work, and Kohei, who was here too, on really trying to understand. So this is very much the semi-analytic, sort of simple, not the big cosmological box. Of course, we've had Lars, we have Romil, we have many different groups, computational groups, Deborah Sajaki. People have been working on Tiziana Di Matteo, on trying to do the big full box cosmological problem with AGN feedback and galaxy formation. But this is just people who work on this kind of track that I've tried to develop to show you of model building. Okay, so, by the way, the Ostriker there is Jerry, not Eve. Just wanted to clarify. Okay, so as I said, the goal of this sort of demographic approach is to model populations and do it very much in the context of the dominant structure formation paradigm, the lambda CDM model. So the idea is to combine the study of these sort of phenomenology in individual galactic nuclei and kind of apply it. So this is sort of the general outline. I'll just kind of go through each of these pieces. And so first, of course, is to show you, I'll just go through this really fast because, you've seen the motivation for the impact of black holes on their environments, the outflows. We've seen many beautiful pictures and of real sources as well as simulated sources. So just to quickly remind you that although the supermassive black hole mass in galactic centers is really, really tiny, its gravitational influence is limited. It's limited into a small region of influence, which is of the order of a few parsec-ish. However, it's the energetics that really couple this small parsec scales to large scales, kiloparsecs, several hundred kiloparsecs even, as we saw, that is of interest, right? So, so we've developed these scaling relations. And so, remember, I keep reminding you, this is for a single nucleus, and we had a model. The question is, these scaling relations that we have derived, are they, do they evolve with time? That's a question we want to ask. And how will we know that? We will know that if we apply a static version of this relation, and we are not able to match, right, over cosmic evolution. So I think the gaps will start to show up. That's the goal. That's why this modeling has such rich dividends, because you start seeing the gaps quite easily. And of course, you also want to understand a deeper question, because you have the sort of the context in which these black holes grow. You can try to investigate when these correlations are set up, and we can try to address questions like whether this is it a real correlation, or is this like a consequence? And you may remember the question that was asked last time is like the M sigma relation. It could be just a consequence of the merging history. The statistics of merging and the central limit theorem will give you some kind of correlation between the central object and the inner regions of the halo that it's sitting in. So that's something we also would like to investigate, so we can play in these models. And as I said, the key goal is trying to disentangle sort of nature from nurture, if you will, seeding from what happens later. And so, and we can see how well we model the properties because we have a lot of observables that we can match. So first, to just quickly remind you that black holes impact both really, really small scales and larger scales. So there's some really beautiful ALMA data for NGC 1433 that you see outflows, you see a nice molecular disk. And on the other scale, on very large scales, in the Perseus cluster, this is data from the dying gasps of Hitomi, and earlier data where you can see these shells that presumably are these remnants of the kinds of outflows that I was talking about. But remember, we looked at the progress of the outflow solution. We looked at the velocity, and we saw that even after the AGN switches off, you sort of slow down. But you have a period when the wind sort of outflow keeps going. So you can have many episodes, and if AGN activity is episodic, which we think it is, then you can have many episodes. So you could have a bunch of shells, for example, that are seen in the X-ray in this Chandra data. At least it's interpreted as that. And you've seen the versions of these plots from me and from other people. I think when Rachel talked about her projects as well, she talked about some of these empirical correlations that are seen between the mass of the central black hole and the host galaxy that they're sitting in. So there's the galaxy bulge mass, black hole mass bulge mass relation, there's the bulge luminosity relation, and then there's the M sigma. And so for most for theoretical physicists and experimental physicists, there's too much scatter here, but for astronomers, it's really a rather good correlation that can really guide us because we're much more tolerant of scatter. So the goal here, as you noticed, this relation per se is something that you can get fundamentally one of three different ways. Either make an argument with the unbinding of the flow supply from radiation from the black hole itself. Remember, that gives you a sigma to the fifth-ish. And then you could argue self-regulation from momentum-driven outflows. That gives you a sigma to the fourth. Or you could just say, well, even just the central limit theorem in the context of the merging hierarchy gives you sigma to the fourth. So this relation is something that is actually naturally arises in any scheme that we adopt. So a relation between, the question is the slope, the amplitude, and the scatter, right? And what information is really in the slope and in the scatter. So, and this is, of course, I should point out, right, as you all know, these are for quiescent black holes. These are for nearby quiescent black holes. And the question is whether there is any additional information in the scatter about either the physics of accretion or the initial conditions for the seeds, right? So that's what we want to ferret out from the modeling. Okay, why did I have this again? Oh, I guess I just like this version of the plot because you can see the errors. So, okay, so some of the other observational constraints is sort of the integrated contribution from the emission from a population of supermassive black holes. As I mentioned, the integrated contribution from the X-ray gives a cosmic X-ray background, and that is extremely well measured now, the shape and the amplitude. So that's the green curve with the dots. And we have a really good model, which consists of two sets of populations of active galactic nuclei over redshift. And the key features of this population are, roughly speaking, they map onto the two accretion models that I talked about. One in which you have obscured accretion, so you could have radiatively inefficient accretion, but fairly rapid black hole growth. For example, at high redshifts, you could have a lot of obscured growth. And the other one is unobscured accretion, which is roughly consistent with the thin disk kind of model. So that's the other reason we think that looking at these two extreme accretion models kind of brackets what we want to study, right? Okay, and so aside from the integrated emission, so this is over cosmic time, this is measured, we're also increasingly starting to push the frontier of how far out we can detect these accreting sources. And we have been, over the last decade, thanks to the Sloan Digital Sky Survey primarily, and other surveys like UKIDS and so on that have followed afterwards, detected a population of quasars and a redshift bin of 5.5 to 6.5. So initially it was one or two very bright quasars, and over time we realize now that we have a population. So we have a luminosity function that is now really pushing out into an epoch when the universe was a fraction of its current age. And that has brought some interesting problems to the fore. First is that when you detected one or two odd bright quasars very early on, remember in the context of the accretion paradigm, it suggests the high luminosity of these sources, the fact that they're detected at all, tells you that they're most likely powered by extremely massive black holes that were already in place at that redshift. So in lambda CDM, as you know, there's a fluctuation spectrum. And so you can always accommodate a few freak sources. You can always say, well, they're in special places, whatever. But it turns out that we are actually detecting a population. So you need a more systematic explanation for the population rather than saying, oh, it's happenstance that this particular peak, high significance peak, is extremely gas rich or whatever, has a particular emerging history that enables very rapid growth, so on. So this is sort of a new kind of feature that has been added to our inventory of requiring an explanation that fits in with the rest of the scheme. So these are the cases. There are several cases now. As I said, there's a population. And in fact, now we are even pushing to redshifts beyond 7. So we have a handful of sources there now. And the masses inferred for those black holes, even up to 10 to the 10. And one could argue whether the methods they're using, looking at lines, is that really, how robust are those masses? They couldn't be off by 3 orders of magnitude, okay? So they could be off by a factor of a few at most. So the requiring very massive black holes to have assembled by redshift 7 when you were sort of 800 mega years after the Big Bang, that is still a feature that has to be accommodated by our models, even if if those masses are slightly off. Okay, so the other very, very interesting data set that came out of SDSS, and that was a real challenge for us modelers at the start, and it really forced us to refine our models, as I'll show you, right, in a bit, is the masses inferred, the black hole mass function inferred for the broad line quasars. And I think broad absorption line, I think Rachel talked about BALs, right, yesterday a little bit, yeah. So the BAL quasars, and now we have constraints on the black hole mass function, black holes powering these BALs, all the way from 1.5 redshift to 4.5. And this is the bulk, this is the action epoch in the universe. This is when everything is really happening, right? A lot of the time in lambda CDM is sitting here, and this is where the peak of star formation activity, all kinds of violent action in the universe, shaping the universe, really happening in this epoch. So it's very important to have models that kind of match this very critical stage in the assembly history of black holes. And that has actually been a huge challenge. So one other kind of new sort of observational constraint that has proven to be tricky to model. We're not actually completely done with figuring this one out, but I'll show you how far we've gotten at the moment. And that is, remember, the integrated X-ray background. Similarly, you have an integrated cosmic infrared background. And the cosmic infrared background, and we saw that when we looked at template toy AGN spectra, you see that there is contribution both in the X-ray and the infrared. So the sources, they should be, same population contributes to both. So unsurprisingly, you take the cross-power spectrum, you see a cross-correlation, but it turns out that there's sort of an excess at large angular scales. And the question is, is there a new population of accreting sources that we don't have, or do we have the spectrum slightly off? Whatever. This is worth investigating. So the one suggestion that was made by Andrea Ferrara's group a few years ago is that maybe you have an early population of massive black holes that are not part of our census right now, and I'll show you what these candidates could be, and maybe they are contributing, and that can kind of explain this excess. So at any rate, we now have a huge bunch of observational constraints that our models have to optimally satisfy. And so, this what did I want to say? I want to say a bit more about with these sources. These are also basically they're faint infrared sources. So M greater than MAB greater than 25. So this is from the stripe 82. So it's about 100 square degrees. So it's not a small, it's not like CDF South or something. It's like from a large patch. And you actually see no correlation between the XRB and the IRB for wavelengths less than 1 micron. And these are basically very optically faint sources. If you try to see optically what are these guys, anyway, so we'll come back. I mean, this, as I said, the reason I wanted to say something more about it is that's been a challenge. Modeling that has been and remains a challenge at the moment. So let me now move on to giving you a sense of where we are at in terms of our understanding of the formation of black hole seeds. So black holes actually, traditionally, right, we have believed. So, you know, I have to kind of show you this high-tech view graph, which is an oldie and a goodie. And what this shows you are the various channels with which you can end up making a black hole. So you can start out with your usual, the most usual pathway is, of course, through star formation. So you have a gas cloud, form stars, the stars live out their lives, and depending on the IMF that you start out with, anything more massive than 8 to 10 solar masses is going to inevitably give you a black hole. Then you could form a cluster of stars, you could form a dense star cluster, you can form a bunch of massive stars. So, you know, basically you can see the many, many routes that would ultimately give you a massive black hole. The question is, which of these are cosmologically viable at the earliest redshifts, right? Of course, they could be operating at later times too, right? There's nothing here that tells you. The only thing is whether you have the right cosmological conditions in the environment, basically gas supply and the kind of dynamical environment that's needed for some of these. So, so my sort of pet idea for the last 10 years or so has been to look and examine that one channel that I've marked out on that diagram, where kind of it's a channel where you do not go through the formation of a conventional star, but you directly collapse to a black hole. So these are called direct collapse black holes. And I've been very excited about them because one interesting feature of this channel for forming black holes, because of how this picture is developed, as you will just see, the seed mass is proportional to sigma, the velocity dispersion of the dark matter. So here is a formation channel in which there's an initial correlation already set up before feedback, before anything else, just in the formation. You set up an initial correlation between the black hole seed mass and the environment via sigma. Okay, so to me, that is why this channel is so interesting, because it's fundamentally different from the other channels, where, you know, the M sigma relation that you see is set up post hoc because of feedback processes, either remember that unbinding the disargument and so on and so forth, right? This is starting off initially. In the initial conditions itself, we are setting up a correlation. And so this is a model I have therefore always liked, because you want to propagate this model down and see, do you dilute that correlation? Do you make it stronger? What do you actually do when you have an initial correlation? And we'll see that it's very sort of interesting. So the broad-based picture, and I'll go into a little more details in a little bit, is that, you know, start out in the early universe. You have baryons, this is pre-galactic. You have atomic cooling halos, redshift 20-ish, 10 to the 6 solar mass dark matter halos. You have gas that collapses, settles down into the sort of this pre-galactic disk. And then this disk becomes gravitationally unstable, and it gets unstable with sort of globally Q unstable, and because of, say, some axisymmetric features like bars within bars that develop, and you remove angular momentum much more effectively, and therefore accrete very rapidly with this instability, global instability, to the center. It's really like the vortex when you're in a bathtub and you pull the plug, see that vortex, that kind of idea. And basically, you can see that in this kind of model, the angular momentum distribution, we are able to pull in, how do I establish this initial correlation between the mass of the seed and properties of the halo in which it is forming? You can see it naturally comes out that the angular momentum of the dark matter halo that sets off this process matters. The gas reservoir matters, how much gas you have you actually formed the disk. And of course, then the dynamics of how the instability progresses. And then it's cooling. Because what you want to do while all of this is happening, you want this halo to be quiet, not fragment, and not form stars. Essentially, you've got to suppress star formation, right? So you suppress cooling, suppress star formation. And the reason it's all very easy to understand at early redshifts is because, so these epochs, because, it's really atomic cooling. So, it's atomic hydrogen, molecular hydrogen really are the main coolants. And you know that, molecular hydrogen is slightly pesky. So basically, you need to either prevent it's more efficient coolant. And since we don't want to fragment and form stars, you either want to suppress its formation or have something that will dissociate anything that is formed. And you automatically know from the energetics that basically photons in the Lyman-Werner band, like 11.2 to 13.6 eV, will dissociate molecular hydrogen. So what would be nice if for this setting to work is that cosmologically, if it happened in a halo that was in the vicinity of another halo where you form stars, basically something that will give you the external Lyman-Werner radiation. Where's the stick pointer? Oh, it's here. Okay. So, and then, so this is sort of just a rough outline of the model, and I'll delve a little bit more into it. So at the moment, this is our current understanding of how you form black hole seeds. This is schematic. So the light seeds, which we all refer to now as light seeds, are remnants of POP3, which are the first stars that form. And many, many years ago, Tom Abel, who's one of my contemporaries, and Rachel's contemporary, we used to always tease them because they were doing first star simulations for like 5 years, 10 years, right? We were like, when are you going to make the second star, right? I mean, can you move on? So it turns out when the codes got better, there was a really good, then we believed that the first star was extremely massive, right? So this would be like thousands of solar masses or whatever. It turns out when the resolution improved, these codes improved, you actually don't form one star, you form a cluster of stars, right? And the masses of the individual stars therefore came down, which means the remnants are going to be a lot less massive. So optimistically, the remnants that you will have for that population tends to, say, 100 solar masses-ish. And I'll show some of the issues that we have with this channel. Every channel has its limitations and constraints. And so this one, the key thing is, of course, the uncertainty in the initial mass function of the first stars. And then I'll show you a little bit with simulations, with ENSO simulations from John Wise, Abel, and their groups, to show that it's actually a challenge to grow black holes, the light seeds in the cosmological setting, even down to, say, redshifts of 6. Because remember, 6 is sort of the stage at which we would like to see how easily you can assemble a 10 to the 8 solar mass black hole. And also the sort of the time scale that's available to assemble these monster black holes is shrinking because of optical depth constraints from Planck most recently. So if you look at massive seeds, so you can end up with slightly more massive seeds in sort of two broadly speaking, two routes. So one is, of course, as I said, now the simulations suggest that you form dense nuclear star clusters. And so you could form a dense nuclear star cluster and eventually end up with about 8,000 solar masses. So you can have an amplifier where you have a dense environment, and somehow the remnant little black holes merge, you get 1,000 solar masses or so. I mean, and there are tweaks to each of these scenarios, like, minor changes that you could do, new dynamical processes, some really nice, clever stuff that you can see that would push you on the route, but eventually it will give you something like 10 to the 3 solar masses. So, and then, of course, this is the direct collapse black hole scenario. And here, a lot of the physics is still not quite done. And one key piece of the physics that's not really done is the details of the stage. And I said, oh, you just funnel the gas into the center. But yes, and then how do you actually get the compact object? How do you get the black hole? Is not fully understood at the moment. Wouldn't you agree, Andrea? Well, I think I'm being generous by saying fully. It's not. It's very poorly understood at the moment. Anyone can come up with anything that makes sense energetically, dimensionally, and we're like, okay, maybe we'll proceed from there. But by and large, I'll show you what we think likely happens. So here we end up with seeds that are about 10 to the 4, 10 to the 6 solar masses. And the nice thing is we're golden with this seed mass range with explaining the quasars at redshift 6 and beyond. Okay? And as I said, the challenges here are that in order for the direct collapse seed channel to form, we need very explicit conditions, cosmological conditions. So you need metal-free gas, as I outlined. So you can see immediately that's going to be a very rare channel. It's going to be rarer in terms of abundance than this channel. And then there are, of course, as I said, interesting hybrid ways. One of the interesting hybrid ways is to obviously start out with a light seed and for the light seed to then get amplified, to have its mass amplified over a very short period of time, very rapidly at high redshift, with super Eddington accretion growth. Okay? And so what that means is basically by redshift 15, you could end up with a seed that is 10 to the 4, 10 to the 5 solar masses, like your DCBH. So you can have an early amplification processes, and people have worked on it. I worked on one possible case. So what we think happens in the universe is obviously a combination of light seeds and direct collapse black hole seeds, right? The more massive seeds. And and I think I mentioned very briefly that there are really no stringent constraints on this sort of primordial black hole scenario at the moment. Okay, and in terms of the from simulations, so this is work from Hirano and collaborators. And so what this roughly shows you, the sort of the dotted histogram, is the IMF of the population 3 stars, right? And so this is from their latest and greatest simulation of following gas collapse in the early universe. And so roughly, this is sort of the range of the IMF, and it's consistent with what I just told you about the remnant masses, seeds that you end up with. So what are the issues with starting with light seeds to explain the most massive end of the black hole mass function at 6? So the light seed channel, with the growth prescriptions that we have, as we'll see, can adequately explain moderate mass black holes at every epoch. Okay? So starting with light seeds, you can explain how you can produce a 10 to the 6 solar mass black hole at redshift 7, 6, 5, 4, 3. You can really explain the sort of the median black hole mass at all epochs. So that channel is sufficient. However, it's the most massive end that we are now trying to explain. So it has to be an essential ingredient of our model because we want to explain the whole population. So here is a slice of a simulation from one of John Wise's students that was just published last year. So these are the sync particles where they're following one of these primordial clusters, POP3 clusters of stars. And what they find, because of the dynamical interaction of these black holes and the environment that they're sitting in, so this is like a rare high density peak, high significance peak, a 3 sigma peak at redshift 20. That's the region that ends up forming these. So what they find using the adaptive mesh refinement code ENSO, that roughly very, very few of the black holes actually end up being sort of sitting centrally. Many of them are distributed. They get distributed out to the virial radius. So it's very hard to actually have one central black hole, to assemble one central black hole cohesively that's even going to be 10 to the 7, 10 to the 8 solar masses. Okay? And so this is at redshift 15 already. And then things get scattered out more and more as time goes on. So by redshift 6, you definitely don't have a winner that is sitting, one that's sitting in the center that has grown tremendously. And they've run these simulations down to 5 at this point. So the other thing they can do, obviously, in these simulations, which is track the growth in mass of these particles to see how much these individual black holes are actually accreting from their environments, right? And what they find is that by redshift 8, they have a halo. It's a really massive halo, 2 times 10 to the 8 solar masses dark matter halo that's hosting all of this. There are about 25 of these black holes that we saw, this cluster, and you accrete very, very little by redshift 8. Okay, so they are just not in the right places for optimal accretion, the light seeds. That is to produce the most massive black holes by redshift 6. This is fine. I mean, and these guys are going to produce the 10 to the 6 solar mass black holes by redshift 3, whatever. So, I'm not ruling out the light seed model. It's just the light seed model cannot explain the entire population. Okay? And so these are the reasons. So then there's this model developed by Devecki and Marta Voluntari, in which they argue that you could form these dense nuclear star clusters, as I showed you, and then basically you could form a very, very massive star from the collapse, and then you could end up with a black hole that has a seed black hole that's about 1,000 solar masses. And then, we looked at another possibility, another scenario where we could start out with a light seed, and can you amplify its mass very, very rapidly? Could you have super Eddington accretion for a brief period of time? Then we worked out what are the conditions that you need to do that optimally. And this was sort of a cute mechanism, sort of a dynamical mechanism. This was work done with Tal Alexander. So you have a black hole seed that is bound to a star cluster, and it's immersed in ubiquitous sort of dense cold gas. You have gas flows. And the key here is that the black hole, the remnant black hole, is basically random walking. It's not at the center of the dense star cluster, but it's random walking through accreting gas and growing. And then eventually, when it becomes the most massive thing, it settles down in the center. So here, what we are exploiting is that the high gas opacity will basically trap the accretion. You can see what you want, right? Basically, you don't want an accretion disk to form. That's why we are sort of making it move around, right? And so you want the high opacity in the gas to trap the accretion radiation, and the random motion should just suppress the formation of a slowly draining accretion disk, right? And so when you have this setting, you actually find super exponential growth. And in this setting, we are assuming that the gas and the stars are actually virialized, and so this seed is just like a test particle in this system, right? And it's an equipartition with the stars, and so it's subsonic motion. So you can find out all the conditions that are basically going to prevent you from forming an accretion disk, right? And so what you find is this is one easy way in which you can circumvent the Eddington limit and amplify an initial light seed to 10 to the 4, 10 to the 5 solar masses by redshift 15. So basically what the seeding work is showing us so far is that as long as you have an initial black hole seed with a mass of about 10 to the 4 to 10 to the 5, no matter how you got it, remember that's partly one of the problems with black holes, right? You have no idea what went into the assembly of the black hole. We have no information about that. So as long as you've produced a seed that's 10 to the 4, 10 to the 5 solar masses by redshift 15, you have a small population, right, that you can then explain the entire population of black holes, including the brightest quasars at redshift 6. So that's what you need. What you really need is 10 to the 4, 10 to the 5 solar mass seeds by redshift 15. And you can get them by hook or by crook. You can start with light seeds, you can start with massive seeds, start with light, amplify, and so on. So this is just a quick schematic to show you that we've we can now start doing simulations for some portions to check out some of the assumptions and some portions of this direct collapse scenario. And so, for example, we can actually track the formation of these small-scale disks, and we can track the dynamical stability of these disks, and we can start resolving the flows to the inner regions. And remember, I told you a lot of unknowns rest for the DCBH channel, rest in the final object, like how do you actually get the black hole? And this is sort of our current understanding. So it's really like, having sort of the envelope of a red giant star. So you have a convective envelope, and then you have like a black hole, that a very compact region in the center, and that you are slowly sort of accreting and growing this very, very rapidly. This is sort of what we believe. This stage is not resolved in any simulation at the moment, and it's not clear how soon this is going to be tractable, because this is complicated, because on these scales, you actually cannot do it's not a simple hydrodynamic problem anymore. Your magnetic fields will be important, all sorts of things will be important at that point. And so I just wanted to show some work from other groups. So this is Mitch Bagelman and his collaborators have also started looking at the inner dynamics. So these are some simulations from my former student, Andrew Davis. And then this is another group in Cambridge by John Reagan and Martin Hainault, and where they have also started, having access. You can see parts of these are simulation size slices that show you we can get up to here. We can get up to this disk, and we can see how the disk can become unstable. But this stage we don't yet. Yep. Yeah.
I just wanted to ask this way of forming black holes through direct the way of forming black holes through direct collapse. Can this be prevalent in
At late times? Yeah, that's a great question. The argument has been made that the conditions that you really need are you need pristine gas, right? And you need, maybe you need this Lyman-Werner radiation to keep it pristine. The question is, of course, people like Hyman and Raul Jimenez have made what I think is a slightly crazy argument, which is that even at late times in the universe, you can have pockets of gas that are pristine. The question is, that is modulo our understanding of mixing and chemical enrichment. So I don't know how viable it is really to, I don't know, Andrea, do you have any comment on that?
Well, it's not only that, you also need to have some strong UV field nearby.
Right.
So there are a number of conditions that
It's kind of hard to arrange all of them, but theoretically there is, if you can arrange those conditions, this channel can follow, even at late times. And it does in principle, and it doesn't therefore have to be only a high redshift phenomenon. But it's actually very, very hard. It's hard enough in the early universe because the sites are so rare, even in the early universe, right? So, okay, so just to condense everything that I've said about the seeding and where we are at, you can, there's the channel of massive black hole seeds, direct collapse black hole seeds. So these are the conditions that you need. You need to suppress molecular hydrogen cooling, and you need to have these massive, relatively massive pre-galactic disks, and which will have axisymmetric, non-axisymmetric features in them, like bars and so on. And then you have super Eddington growth, inevitably to give you the seed. Or you could start with a light seed, as I showed you, and you could amplify that. So there's also a very nice scenario, as I said, there are dynamical ways, there are many cute dynamical ways to start with a light seed and end up with a more massive seed. And I just want to point out, there's a very nice model that I like by Nick Stone and Jerry. Okay, so so this is, we've bracketed sort of the two mass scales for seeds. And I just wanted to show you that there's been, there's progress, and people are working on trying to make these seeds and follow through to actually getting a final seed mass, because what you get from the kind of arguments that I've shown you is sort of an upper limit to the seed mass, because there's probably going to be some mass loss by the time you actually assemble the little black hole. So right now, I think this is sort of against state of the art, Hirano and collaborators again. And what they find is that they can form a supermassive star-like object that's about 34,000 solar masses, and that guy will give you a direct collapse black hole. So as you might have noted, right, this mass range of 10 to the 4 to 10 to the 5 solar masses, which we often refer to as the intermediate black hole mass range, so stellar mass compared to stellar versus supermassive, as an observational population, they have been quite elusive. It's been really hard to find them. But there have been some interesting recent cases. This was last week, and I thought this was very, very cute. And so which is a scenario in which you have two galaxies, so Gal1 and Gal2 have had some merger at some point, and then there's a source here shown in green that actually had, they measured a tidal disruption event. So this is gas or stars that have been captured by a black hole, has a very characteristic time scale for that light curve for that flare, t to the minus 5/3. And this, they went back and they saw this flare as predicted in the X-ray data in Chandra before they see it in the optical. That's predicted. And they saw it in the 2005-2006 Chandra data that this particular source had brightened considerably, and then now it optically brightened. And so they are arguing that the luminosity of the tidal disruption event suggests that this guy is an intermediate mass black hole. So what is very nice about this detection, the reason I'm making a point of this, is we've been claiming that it's challenging to find intermediate mass black holes because if they're sitting in the galactic center, it's really hard. There's lots of stuff happening in the center. So this might be, so current models are also suggesting that there should be a large population of wandering black holes in the outskirts of galaxies and in the halos. And therefore, if off-center tidal disruption events mark the presence of an intermediate black hole, this might be an entire new way to start detecting and filling in the intermediate mass black hole range. So this was the state of affairs a few years ago, like 4 or 5 years ago, in our attempt. So remember, part of what I'm trying to show you is the power of these models is you can refine them. Once you understand and you don't match with the data, you find a gap, you can refine them. You can go back and understand whether is it your accretion model that was mismatched to what you were doing, that's why you don't match the observations. Is there something peculiar about something that's happening at high redshift, low redshift, so on. So about 4 years ago, when we ran these models, and at that time, we had only one accretion model that we looked at, which is the Eddington limited model. It's a thin disk model. We said, okay, everything luminosity produced is always proportional to m dot. And what we found that essentially you needed black hole seeds heavier than the POP3 seeds at high redshift for these redshift 6 quasars. I've been going on and on about them, right? So in order to really match those luminosity functions, you needed another channel to make the seeds comfortably, right? The only thing is, you can still make them with light seeds, but then, they have to be sitting in the right places for long enough, so, whatever. And what we found is that brief periods of super Eddington accretion early on could be very, very helpful to match the constraints. You can see where this is going. So this was the motivation to then develop a new accretion model that takes into account super Eddington accretion to investigate that, right? And so we also found that basically you need very inefficient feedback coupled the way we did. So there's this sigma to the 4th kind of sigma to the 4th, sigma to the 5, the momentum-driven and energy-driven feedback. Yes, we needed feedback, but we needed it to be not too efficient. So there was a tuning that was needed in the efficiency of feedback. Otherwise, you truncate the growth of black holes prematurely, and you're unable to match the high mass end of the black hole mass function. And there was another thing that was pretty evident in trying to match the data of the broadline quasars. Remember showing the mass function of broadline quasars, redshift 1 point from SDSS data, 1.5 to 4.5. We were unable to match it unless we added in a long-lived, oozy, steady accretion mode, a growth mode that is not linked to mergers. Okay? So much of the prescription in our models, part of the power of using the lambda CDM framework is we know structure assembles hierarchically and that you have mergers of halos, galaxies, and therefore they're black holes. And the way we've constructed these models so far is that during a merger of halos and galaxies, there's a huge amount of gas that's delivered to the center. So you have a merger-triggered accretion episode. So you have like a huge piston that goes in during the merger, right? And so it turns out, and those were the sort of models, and that was sufficient given the data then. But once the SDSS mass functions were provided as observational constraints, we found that you needed a long lived. So, and this is nice because conveniently around that time, Hopkins, Phil, and Quartert came up with a nice model in which they showed how you could have disk instabilities. And I think Mordechai has worked on that too, to look at how you could feed in a sustained long-term way at a very low rate. But it's significant because of the time averaging over which you can add mass. So obviously now this has to be an ingredient. So with this guidance, what I'm doing for you is showing you the process of how we refine the model. So these are the ingredients we started with. And now it's clear we need a couple of new ingredients. We need brief periods of super Eddington accretion, and we also need a steady accretion mode to describe the entire population. So let me first, before moving on to the population, let me spend a little bit of time, because it's some really nice work and it's new work, on modeling early seed growth. So the early phases, you form the seed, by hook or by crook, you've somehow formed either the DCBH seed or the POP3 seed. The question is, then what happens? Remember, all the action, we want a lot of action in terms of mass assembly for this black hole to happen between redshifts of 15 to 9 or 10, right? And so the question is, okay, you formed the seed. Now how does it grow? How does the growth proceed? Obviously, we are doing this to investigate the two accretion models to see what the consequences are for early growth. So this is a code that was, this is done with a simple code, but called GEMS that Fabio Pacucci, who is a former student of Andrea's Pisa, developed during his PhD. And we adapted that for the problem to see what the early growth phases could be, what the output spectra would be, and can we discriminate? Does this really happen in the early universe, right? So that's the goal, is to then try to make some predictions as well. So it's very simple. As I showed you, you started off with a seed mass, and then you have the gas profile right around it that you can model either with an isothermal or what have you, any distribution that you want. And then you calculate the output spectrum. So obviously you have gas accretion from the accreting source. And then you have the scattering and absorption that is coming from the gas envelope outside, right? That will modify the spectrum. So we have, as I showed you, we put in all the usual components for the disk and the corona and so on. And the post-processing, so this is not a code in which the post-processing is done using the publicly available code, Cloudy. And essentially, we look at the gas flows across the Bondi radius. This is the radius where the sound speed, the velocity matches. It's the sort of the boundary between supersonic and subsonic infall for gas onto a compact object. And so at high redshift, we start out with a black hole seed, an initial seed that is located, already formed at the center of a dark matter halo with a total mass of about 10 to the 7, 10 to the 8 solar masses. I think the actual data I'm going to show you are for a 10 to the 8 solar mass halo. correspond to sort of a virial temperature of about 10 to the 4 Kelvin. And so we then analyze the sort of accretion on scales that are comparable to the Bondi radius. And this is a radiation hydrodynamic code. Let's see what else. They are the source spectrum pieces. And this is the fun part. And so part of trying to understand how to incorporate super Eddington accretion into the larger, the full cosmic time models was this investigation to see what happens at early times when we implement it. So there are these two accretion models that you saw that are motivated by the kind of feedback the black hole provides. So this is the thin disk, the alpha thin disk kind of model, where you have the luminosity proportional to m dot, and then you have the obscured accretion, super Eddington flows, radiatively inefficient flows. So we model both of these accretion modes. And so what's really different in the standard sort of geometrically thin disk, it's optically thick though. You have moderate rates up to the Eddington rate. And the luminosity, output luminosity is produced, it's a very radiatively efficient situation. So most of the luminosity produced in the inner regions is able to escape, right? And it's escaping from the inflowing material, and you actually see it, right? So that's your standard Eddington case. And this relation is actually kind of linear. So in the super Eddington scenario, on the other hand, what you would really have, the so-called slim disk solution. The structure of the accretion disk, it's also geometrically thick and optically thick. And it's very radiatively inefficient. So what happens is only a fraction of the emitted photons are basically advected back into the central object, and they're unable to escape, right? So the efficiency of the radiative feedback in this case is actually much lower. So basically, the radiative feedback is less efficient in disturbing the gas flow, the inflow, dramatically. So let me show you. So these are the components. So we start out, these are the ingredients to compute the emerging spectrum. And what we do is over time, we are tracking the growth history of this seed. Okay? And we obviously want to know what the luminosity is, and this is the mass that is assembling for the seed. Okay, so we can do that. So what do we understand from this? So what is really crucial is from those simulations, starting out with different seed masses, from so the light seeds versus massive seeds. And so this is actually work from other groups as well, and this particular one is Kwang Ho Park's work. What we found is that the growth is sort of faster for initial black hole seed masses. And in the feedback limited mode, right, which is the sort of, there's an inefficient, there are sort of two modes for the growth of seeds early on. One is a feedback limited mode, which operates for the light seeds preferentially. And only a small portion of the gas, like 10 to 15% is accreted, the rest of it outflows out. Okay? So we can track that, we find that. And then we find in the gas supply limited mode for massive seeds, in the super Eddington case, so the outflows, you don't lose a whole lot of, you pretty much catch in most of the mass, that about 80% or so makes it in. And there's low radiative efficiency, and that this kind of operates for the massive seeds very, very nicely. And of course, what really does matter, right, is the large-scale gas distribution. And once again, like that analytic model that I showed you, there are transitions that happen between these states, and they happen when the gas mass reaches a critical mass. And if you remember, I talked about how when the black hole mass is equal to the bulge mass for it to sit on m sigma. So we see that, ab initio, we see that sort of emerging here in this simple simulation. And so the details are, it's very interesting, but since it's just one ingredient in our model, I'll keep moving on after giving you the key results. And then this is another nice paper that Fabio led this work, where he was able to, it's a reframing of the same physical situation, which basically shows you that direct collapse black holes basically grow very, very efficiently. And the parameter space that's relevant to determine where you land, right, in this simple context of starting with the initial seed. Remember, we are not making the seed here. I just want to clarify. We made the seed already, and then we are tracking early growth. So is really the environment, the properties of the environment, the gas density in the inner regions, and of course, the seed mass. OK, so this is all well and good, but what are the observational consequences? So we've now understood that we can make seeds. We kind of understand their early growth. OK, great. So is there an observational signature that we could use to test this early growth model? Right? So it turns out that there is a cute sweet spot. And that has to do with the fact that when you look at how the direct collapse black hole is formed, and it has then grown, as we just saw. And remember, I told you the optimal site for it is where this halo that is hosting, that will eventually host a direct collapse black hole, will be irradiated by radiation from a nearby halo. So it turns out that the optimal sites are satellite galaxies for a galaxy that has already formed, let's say, a POP3 population, right? And because merging rules, this halo that contains the DCBH, the one that we just saw, embedded in the gas with its early growth, will merge with that parent galaxy very rapidly. And you will have a very peculiar kind of object, an unusual object, in which the mass of the black hole is comparable to the mass of the stars. And the spectrum of this object will be dominated by accretion onto the black hole rather than the stellar component. This is a transient object because it will immediately merge with other galaxies and so on. And we remember we are rapidly moving towards the M sigma, well, not rapidly, we're moving towards M sigma, where remember the mass of the central black hole in the Milky Way, right, remember there's a factor of 1,000 different. The central black hole is undermassive by a factor of 1,000 compared to the stars in the bulge. Right, but this is the inverse. But it's a transient. And that stage has very, very important consequences because of the peculiarity of the spectral properties of this object. So we call this very unimaginatively obese black hole galaxy. And so then you can examine. So as you can see what I'm doing, right? I'm starting with light seeds and starting with heavy seeds. I'm moving them forward little by little with 2 different accretion prescriptions. I'm looking at early growth. And so we can see what happens when you have a POP3 remnant, and it also will merge, and then it will form an object. In this case, the mass of the black hole is going to be comparable, is going to not be comparable to that of the stars. The stellar component is going to dominate a little bit more. So here it's much more dramatic, the mass contrast between, and therefore the spectral signatures will be dominated by accretion here, not as much here, as we'll see. So this object, right, so there's another cute schematic to just show you. So you have a pristine atomic cooling halo. You have a galaxy where you formed a POP3. This guy is, say, a satellite. So from the statistics, we think that is the best sort of site in the lambda CDM game. And then you form this halo that has a direct collapse black hole that has some early growth, early amplification to, say, 10 to the 7 solar masses or so, merges with this guy. And of course, here you can merge with the stellar population with differing metallicity. So we're just trying to play to see what are the signatures that will impact downstream the observed spectrum. And then you have the population 3K. So what we want to do is to see whether there are features that will help us detect these sources in the first place to test the model. And second, discriminate between these sources, right? Obviously, that's one of the And we wanted to do this to look at early times before there are all other host of dynamical complexities in the universe that come in. So we are hovering at redshift 9. So we've come down to 9 now. And so this is another sort of animation showing you the time evolution of the buildup of that OBG. So you have the stellar population. So here the stellar population is being aged, the black hole is growing. And what is amazing is you find that a lot of the radiation, you get a lot of output in the infrared. And unsurprisingly, conveniently, in the JWST, as you can see, JWST, these objects should be detectable JWST. And what's really happening also, if you notice the X-ray flux predicted in the spectrum of this OBG type object, notice these are the CDF Chandrajeep field south limits. So notice that during the evolution of this object, there are stages where such objects should already be in the Chandra data, which is awesome because they are rare, and we need to have a way to select them. So we'll have a pre-selection from Chandra data, which will help us pick. And then we did the whole tableau, different metallicities, different densities, and so on and so forth. So we have a set of templates, and I'll show you some of the key features of the templates. So JWST should be able to easily detect all these, this stage, this source, when there is a direct collapse black hole seed. Let's try and compare. So let's do the comparison. Remember, the game is to test this idea, is to make a prediction to see whether you can discriminate between POP3, initial POP3 seed, and a DCBH seed. We know that downstream, by the time you get to redshift 6, you're not going to really have too much information about how the initial seed formed. That's going to get scrambled with a lot of stuff. So as early on to the epoch of seeding that we can go and that we can get data in the near future, well, I was hoping next year, but I guess it's slightly delayed gratification, 2021. We should be able, so this is the POP3 seed with the merged stellar component and the standard. So you can see where this is going, right? I mean, I have the accretion model, I have the metallicity of the stellar population that is merging, and I have the seed mass. And I can play with all three, and I can just, I can plan out the parameter. I can map it out completely. And that's the advantage of these kinds of models, that we can quickly do this. It's not like a 6-month simulation. We can very quickly see what's going on. So, and you can understand a lot of what is going on when you look at the relative fluxes in the X-ray, optical, and the infrared. Basically, you see that, when you have higher metallicity, metals basically will absorb the X-ray photons, and you'll have an enhancement in the IR flux, and you have Auger-like processes. We understand roughly what is going on, why you have the spectra that you have. And the bottom line is that you find very infrared bright objects, which should be detectable, as I said, in the current X-ray data for a DCBH seed. A POP3 seed, on the other hand, it's very, very marginal. It's not infrared bright enough to be detected by JW. So that's the range and sort of the flux sensitivity of JW for a 10 kilosecond observation. And also, they should be sort of, these candidates could be there in CDF South. So they would be X-ray bright enough to have made it into one of the deep fields, but they're not going to be infrared bright to be detectable in JW. So I'll show you a few more cases because I am seeing that, oh my God, time is rapidly melting away. Okay, so you can work out the various, you'll have my slides, so you can see that. And also, this is all published, by the way. It's all published work. We published it a year ago or so. So, and the upshot is that, if you have the slim disk versus the standard disk, so we think that you can discriminate not just the seeding model, but also the accretion model with JW data. So let me quickly move on. And we're just zooming in on the infrared part of the spectrum, and I'll just show you that these are the predictions for the OBGs powered by direct collapse black holes, right? And so these are for the zero merging with a zero metallicity stellar population with 10 to the minus 3 solar. And you're still, these are the JW MIRI and NIRCam bands. So these are the windows. You're like comfortably well above. You have a very peculiar spectral shape. So you have this feature that you can use to detect. And so you can come up with color selections in the X-ray IR. And you can actually discriminate these objects from your usual sort of extremely dusty early type galaxies, extremely blue star-forming things, so on and so forth. So you should be able to discriminate them, we believe. OK, so now let me quickly move on to modeling the population. So now we've come down to redshift 9. Let's roll the dice to go down to redshift 0, right? So I just wanted to point out, to remind you that in the scheme, black holes are going to grow in 3 different ways. A merger-triggered burst, right? Steady accretion. So that's the new ingredient, remember, we needed to add. And direct mergers that are going to give you gravitational wave events. So this is a nice simulation. I really like this because it's from, aside from the minor vested detail that it's my former student Pedro Capello's work, what you can see there is that when the black holes, these are 2 spiral galaxies, black holes in them, and when they're actually growing, you can see it flickering in the center on very short time scales. And basically, that's to tell you that that's another element that we're going to include, the flickering. Short time scale variability, to see what that buys us. OK, so what are we going to do in these demographic schemes? We're going to start out with a seed, then we're going to do the merger-triggered accretion, steady accretion, actual merger, follow it over cosmic time. And we're going to try to understand. We are not explicitly modeling the stellar mass assembly. So as I told you, there are sort of, ours is a demographic model. We're interested only sort of in black hole growth. But in the context, of course, in the cosmic context, I think Rachel and others have very sophisticated models in which they consistently follow from the same gas reservoir the stellar mass assembly as well, and can predict all the observational signatures. So these are sort of the features of our model. So it's a semi-analytic model. And as I said, we have feedback from, when I say feedback, I don't mean black hole feedback. I mean, we have feedback from earlier attempts to match the data on the ingredients that are needed. So, and you all know the scheme. So basically, these are using Monte Carlo merger trees for dark matter halos. You seed them, you track them, and you figure out the properties of the population. And you can repeat them for 20 to 30 halo masses many times over. So, and this is the initial seed distribution. So this is the direct collapse black hole seeds. These are POP3 seeds, and we'll be populating the halos from these 3 seeds. OK, so what are the new? OK, where is the physics coming in? So in this story, you have a merger. So you have a merger-triggered accretion episode. The question is, when does the black hole stop accreting? Is there a cap? What mass that the final merged remnant, how much can it grow? That's where the feedback prescriptions come in. The scaling relations for the feedback prescriptions limit the growth during an accretion-triggered merger event, a merger-triggered accretion event, sorry. So the feedback models that we developed that I outlined for you in the last lecture, they are incorporated into this cap. The cap, how much the black hole can grow after a merger. Okay? And so previously, in these models, right, so this is one of the key ingredients in these models, because it's all done in the framework of dark matter halos. You have the halo mass as a function of redshift, which we know very well for CDM. And then from there, you kind of using MoMA white kind of models, a simple model for gas collapse or whatever, you can relate the circular velocity of the halo. And remember, this is the circular velocity of whatever the disk is that's going to form, because that's where our seed is going to form. And then you can relate that to the velocity dispersion of the halo. If you use an isothermal sphere, that's just for the gas distribution, you get roughly a factor of square root of 2. And then you can use m sigma to do the final prediction of what the black hole mass should be. I mean, you track the black hole growth through your accretion prescription, and then you confront and see what the m sigma relation that you get from this scenario. Okay? And you assume that the distribution is isothermal when you're mapping the circular velocity to sigma. This seems like a very trivial thing, but it's a very deep issue. It's a galaxy. It's really making an assumption between the connection between galaxies and halos, right? So it turns out that that is very limiting, and so our new model includes more phenomena, more observational data. So you go from halo mass to stellar mass, and then, as you all saw using the relationship that published by Moster et al., and then you try to use the relationship between redshift and size, because there's a relationship between stellar mass and size. We use that. And then we use the size-stellar mass relation to get sigma. And then we track our black holes through the accretion prescription, and we confront the m and the sigma that we get. So when you do this, and these are all the elements that now, in the version, that the honed version of these models, these are the elements that we need. We need some kind of stochasticity, short-term time variability, because that is seen in the data, right? And you need the different seeding prescriptions, you need the accretion models, and the goal always is to discriminate models. And we're particularly interested in seeding, right? I am at the moment, only because JWST can help us, I think, discriminate. So I just wanted to quickly show you that, how you map the halo to the galaxy, right? You're mapping halo properties to a bulge velocity dispersion. And we want to do it without actually forming the bulge and the details of galaxy formation. So I told you that the mapping was just an isothermal sphere. You relate the circular velocity of the halo to the velocity dispersion of the bulge. So if you do that mapping, that is sort of, as a function of halo mass. For any given halo mass, it's a fixed square root of 2 or something. But as you go on in halo mass, it's that. So it turns out that our model, that is actually a very unrealistic model. Okay, it's incorrect and it's unrealistic. And so our model that I just showed you actually gives you a relationship between halo mass and sigma that looks like the blue curve. And it's a very important, it has consequences for the results, which is why we can actually match. We traced back, and we saw that this is something that matters a lot. So the other thing is that we use an Eddington ratio distribution to sample from, right? So we're not always accreting at Eddington rate all the time. We will draw from the Eddington ratio distribution, because this is observed. From X-ray sources, we have a prior for what the Eddington ratio distribution should look like. And what we did is, in order to allow for super Eddington accretion, we modified the observed ERD and did an extrapolation to permit super Eddington accretion. Okay? Basically, you random walk through this. Then we know that empirically there's a relationship between black hole accretion rate and star formation rate, and many people talked about this yesterday. And so this is from the Romulus simulation. We definitely see that in simulation. There's some sort of correlation, and it's definitely seen in observationally, right? And the question is, it would be useful, therefore, to test an accretion model where the black hole accretion rate is tied to the star formation rate. Right? This is just I'm just showing you the landscape of models, right, that we can build and test. And so this is a feature that the current models really had. You have a measurement triggered, and then for a period of time you accrete, and then bam, you stop. So here we have some kind of stochastic sort of accretion is our implementation, along with variability on 10 to the 5 year sort of time scales. And the 10 to the 5 year, remember, came from the data that I showed you in the motivation for model building last time. So Here are all the realistic ingredients. Here is a list of the models that I'll be showing you the results for. To give you a feel, so we have a model 1, which is a burst mode, in which you have every major merger, a merger of 1:10. And after a dynamical time, the black hole just grows at the Eddington rate, and then it stops as soon as you hit that feedback cap. Okay? And remember those values in the feedback cap, there was an alpha and a beta. The beta index was the power sigma to the beta. Those are really what come from the feedback model. And we have a little bit of latitude there, as we saw yesterday, or on Wednesday. So, and then we looked at 2 kinds of steady modes. So we have a burst mode on top of that. So this is what happens during every merger. But then when you are not merging, remember I told you you need this long-lived steady mode. We actually implement 2 kinds of steady modes. One is when the black hole accretion rate is proportional to the star formation rate. And the other one is you have a power law mode when the Eddington ratio distribution, as I told you, that's derived from X-ray luminosity functions, we draw from that for that sustained phase. Okay? The thing that is missing, the reason this is in white, and it's missing in our model, as it is in almost all models at the moment, is a very poor modeling of the dynamics of the black hole merger itself. Because remember, I want to ambitiously also predict the gravitational wave events. I want to predict, I want to do the whole hook, right? But this is, at the moment, our current limitation. We are trying to understand it. And so the simple thing that we do is we look at the cases where, every time a halo merges, the black holes will eventually merge. And every time a halo merges, only 10% of the time. So this is, again, bracketing, right? And the details of this, of course, of the dynamics of what brings the black holes together is an entirely rich subject on its own, right? So for example, if there's gas that's present in the center, we know that it can affect the merger much more rapidly, that stars can bring them close enough up to separations of kpcs, maybe a few hundred parsecs, and then on much smaller scales, you basically need this circumbinary disk that could help you, and so on and so forth. So, but we just bracket that. We don't actually model that as well. And at the moment, we are looking at delay time distributions, the delay between halo merger and how long it actually takes for the black holes to merge. We are using this particular simulation, the Romulus 25 box from Michael Trammell and collaborators from Washington, to use that prior distribution to do a slightly better job. I don't have the results for that yet. So what we can show, I'll show you, given that I don't have too much time, I'll show you what I think are the key plots, right? So I have an exhaustive set of things that show you with every model, how do the most massive black holes grow? How does your average mass black hole grow? So you get a very good feel for it. So let me just show you a quick thing in terms of a few histories that encapsulate what's the difference between the light and the massive seeds. So as you can see, I'm slightly fixated on the seeding discrimination. So if you look at the mass assembly history, there's a few tracks for a few of the black holes. These are the light seeds, start out with very low masses, and this is sort of how you build up over time. Whereas these are the massive seeds. So notice that the bulk of, there's some early growth, but there's not a whole lot of early growth. There's a spurt out here. So you start life already advantaged. This is not the track of something that's going to explain the quasars at redshift 6. These are the sort of your average guys, right, that are going to end up at redshift 0 with 10 to the 9 solar masses, right? These are the stuff that the massive survey is finding in the centers of BCGs at redshift 0. So these are those tracks. And if you look at the assembly of this mass, not as a function of time now, but in terms of the sigma, you notice that there's a difference. So you can see this as a proxy of the assembly of the stellar component versus the assembly of the black hole mass. So by and large, you can see that when you start life out as a massive seed, you the stellar component grows for a period of time, and then the black hole grows. So these are your mergers, the kicks that you see up. And here you see coeval assembly. So these are some of the features. So you can sit and dissect and understand, and you can understand quite well. I'll skip that. That's just a cute movie, but it's really it's show off rather than too much informational content. So we can just look and compare these various models. So remember, this is the burst plus steady, where this is the power law model. And so this is to show you how this set of assumptions manifests at redshift 0, right? We can evolve everything to redshift 0. And you can see this is the AGN main sequence model in which the steady mode, the black hole accretion rate, is proportional to the star formation rate. So notice this kind of model predicts like a whole bunch of sort of outliers to m sigma at the low mass end. This guy is no good because we should have seen these. It's predicting a much larger overmassive, ultramassive black hole population, which we don't see. We should have seen in terms of selection effects. We should have been able to see those. They're rare, though. They're very rare. So, but I think this model is not looking so good. It's rather shabby. And these guys, this is just the burst. We know that just the burst on its own without a steady is just not an adequate description. And so here you find that there are some signatures that that you can see. And then you can you can zoom in on the two models that are viable, which is the AGN main sequence model, the burst plus steady mode that is modeled with the AGN main sequence, and the burst plus steady mode that is modeled with the power law. And then you can contrast the light and the heavy seeds, and then see systematically what the predictions are. So, there are signatures here. We need to understand a little bit better scatter in the relations that we have adopted. So that's work that Angelo is doing right now. If you add the intrinsic scatter and uncertainty in the recipes that we've put in, how does that affect the low mass end? So then the other thing that we have, quantities that we can match, for example, is a local black hole mass function. So let me quickly show you that, with these various models, you can, so the point is not to produce an exact best match to the data at the moment. It's to understand, of course, we want to match it, but it's to understand systematically what causes shortfalls and let me see. So some models can really be ruled out. So the interesting thing is this is the redshift range over which we have constraints, okay? So this is the range over which we need to match. And then this is what the stochasticity gives you. It helps you model the very small scale changes in slope in the luminosity function. Okay, so what are the two key observables? I'm just going to go over like 1 minute. So the key discriminants, I've shown you that the discriminants are going to be the low mass end of m sigma, high mass end of m sigma, the scatter, and those are likely discriminants of seeding as well as the accretion model. Disentangling them is trickier, as we just saw. But the one key observable that is very interesting is the occupation fraction. It's the fraction of galaxies below a certain mass that contain a black hole. So this has been measured. So the blue is our predictions from our various models, the heavy main sequence model, Paula model. The black is data. So the reds, I think the circles are actually from Elena Gallo for cluster. Sorry, no, that's actually, the circles are Jenny's field galaxies, the occupation fraction, and the squares are from Elena Gallo's work looking at the accreting sources, black holes in the Virgo cluster. She did a survey called the AMUSE survey. And so what you see here is, at the moment, I'm not going to make much of it. At the moment, the heavy seed model with the AGN main sequence, where the steady mode accretion rate is proportional to star formation, looks like a better fit. But what's the fun stuff? The fun stuff is the predictions, right? So now, with the models that work best, matching all that data that we see, we can make a prediction for higher luminosity functions, higher redshift luminosity functions. And so these are predictions from these models. And obviously, this limit that's been drawn here for, there's a proposed X-ray surveyor class satellite called Lynx. And so that's the limit. So basically, you should be able to start seeing differences here. And you might say, oh, that looks kind of small. So let me show you another way to do it that will show you much more clearly. This is the total number of AGN in a deep field, in a Lynx deep field. So you can actually see that you can get, so these are the heavy seeds, light seeds, you can actually start to see discrimination. However, the key discrimination is going to come from LISA, from the merger rates. Okay? And I told you that the dynamics is not as well modeled, but the bracketed cases, right? Probability 10%, 1%, we actually find there's a real difference in the number of LISA sources that are predicted. And so I think that the gap between stellar mass black holes, intermediate mass black holes, and supermassive black holes, so LIGO, LISA, PTA, this whole range is going to be bridged very, very soon. And our goal is to try and make as many, as sophisticated a model as we can make to make as many predictions to see what can be tested. So I'll just stop here. And thank you so much for your attention, guys, and for attending all 3 lectures.
Very pressing questions, so
I'll be hanging around anyway, so you can catch me.
we'll do 5 minutes of very pressing questions. Okay. Yep.
So this may be a very basic question, but is there like any understanding of whether at higher shift, because of the different growth mode of the black holes, that their spin may be different, or is there any way with like decade or 2020 that we have new telescope or surveys that can help us?
That's a good point. As you might have noticed, I really skirted. I never really talked about spinning black holes, right? Because spinning black holes, there's a different efficiency. The spin impacts the efficiency with which for radiative accretion, conversion into accretion. And yes, the spin distribution will have consequences. And the uncertainties, we think that the natal spins are probably random. And then during mergers, you will either spin up or spin down. And other things that matter in sort of really incorporating spin into this framework. It's important and would be great to do it. I think there have been some first attempts. I'm not persuaded yet that we understand it enough to even go for these models. But the reason for that is there's some physics that needs to be understood in much better detail, right? So it's not just that you start with natal spins, you draw from that distribution. We can't do that same game, because what really is going to matter is what is the alignment of the spin of the black hole with that of the inner accretion disk. We think that those timescales are really short, but those kinds of calculations have been done in the context of thin disks. We haven't really done them for thick disks. We don't know yet. Okay? So, and as I said, a lot of the action in the early universe is probably like thickish disks. However, observationally, yes, the spin distribution from the ion K alpha line, we should be able to have an estimate of black hole spins. And at the moment, the observational situation is that almost any black hole, there's a handful for which we have spin estimates, they're all highly spinning. So it's kind of hard to know if this is systematic or if this is real information about the physics, because actually the sample size is small. So hopefully with future X-ray missions, I think Athena should be able to help us with this. And so, going forward, that's an ingredient that you want to include in the modeling.
One last question.
Hi, so for the direct collapse mechanism, it seems very dependent on the Lyman-Werner radiation. And I was just wondering, since there seems to be like orders of magnitude uncertainty in what the flux is for the value at which the halo can collapse, how do you incorporate that into your model?
Yeah, that's a good question. So it turns out there's a new paper by Gillian Bellovery and collaborators, as well as a Japanese group, that actually have shown that you may not really need Lyman-Werner photons at all. That you could do that with tidal torquing. Basically, what you really need is you need to seal a portion with very dense portion of the inner regions of this pregalactic nucleus. And so they were showing that they can make that supermassive star that I showed you, 34,000 solar mass star-like thing. They can make that without a prior source of radiation outside. That just from initial gas collapse, they can make it. So the word is still unsettled. What we do know is that we initially thought that there was a critical value. There was a J-crit that you needed, right? Minimal J-crit. And there was a lot of uncertainty about what that J-crit was and much discussion. But I think at the moment, it's really unsettled. And I think Andrea has been thinking about this recently. Do you want to add anything to that?
No, I think that it's true that, well, maybe I should speak up.
Yes, I think that there's a lot of space for new ideas here because clearly the fact that you need such a high and local announcement of the UV field is something critical for the mechanism. So if we discover that we can prevent H2 formation by other means, like
Turbulence,
this,
whatever.
something else, that would be very, very useful. On the other hand, you don't want to form too many of these things, right? Because
Right, yeah.
we don't see them around
Yeah.
too often. So,
Yeah.
There's also this. There are all
It's
these things
okay
that
for
need-
it to be
yeah.
slightly Baroque, but yeah. But I think, it's a good question because, this is an area it would be really nice to have some new ideas. There's room for both simulation work and sort of analytic work.